We want to know how we got here, in a sense. And part of how we got here is knowing why we're made up of the things we're made up of, what the structure is of the world. I mean, over the centuries, we've gone to sort of knowing basic laws of physics, to then discovering that we were made of atoms, and then that atoms were made of electrons and protons and neutrons, and then that sort of protons and neutrons were made up of quarks. And it seems that, I mean, as we go further, it always seems that there's more. Perhaps not that sort of quarks are made up of something else, but there's more to understanding what's really going on. We haven't really figured out the big picture. It's, in a sense, it's fundamental human curiosity. What are we made of?
What is Eurostar?
Yeah, Eurostar is our dodgy name for a London-Paris collaboration.
Does he still call it Eurostar? That was like our joke. We needed a code name when we weren't telling anyone what we were doing because we didn't want anyone to copy it.
Eurostar is a project with Jon and Adam and my PhD student here, Mathieu, which is designed to find a new way to discover the Higgs.
We have a theory at the moment which works extremely well, better than any scientific theory ever has in terms of the accuracy of its predictions. It's called the Standard Model of Particle Physics. But integral to that is a thing called the Higgs particle, which we have no evidence for other than the fact that it helps us make these extremely accurate predictions.
Particle physics, the standard model as it is, provides no mechanism for explaining why anything has mass. Mass is left out and it's just kind of added in. It's an ad hoc thing, it's not really explained. So the Higgs mechanism gives you a sort of a mathematical way of introducing mass to the universe.
It's actually not that simple to explain what the Higgs is. Imagine you're in water and you can't see, you don't realize that you're in water. When you move around in the water sort of makes it harder for you to move around. And that's like giving you mass or giving you inertia. And there's a field around us known as the Higgs field, or at least we believe there's a field around us, which is called the Higgs field, which is a bit like water. What we want to do is somehow sort of make a little wave in that water and see the wave. We as a field, sort of the particle physics community. And that perturbation is the Higgs particle in a sense.
Gavin is the theorist, which means that he's not tied to any particular experiment. And he spends his time doing more general things like coming up with ideas and studying how particle physics experiments in general can analyse data. And so he's a theorist and he's based in Paris. Jon is my supervisor, so he tells me what to do, I guess, in theory. Jon is what you would call an experimental particle physicist, which means that he mainly works on analysing experimental data.
And what's your job in the team, as it were?
I could make some flippant comment like doing all the work. No. I guess my job is...
Well, you are doing a lot of the work, aren't you?
My job is to write the code and run it, basically. Yeah, I guess my job is to do a lot of the sort of the mechanics, the hands-on part of the analysis.
Between us, me and Adam and Gavin and Matthew came up with what we thought was a good plan of a new way of finding the Higgs that no one had thought of, which is quite a big deal really, because the whole detector discussion of what you do at the LHC has been going on for a decade, or 2 decades I would say, at least since the beginning of the discussions. And you'd think that most things have been covered.
I mean, it's basically, it's a collaboration to really see if we can turn what's an idea of something in principle into reality. The first part of the process was to see if it was realistic and to write a paper about it so as to communicate this idea to people more broadly. And that's now done. So we now have a paper out. It was accepted just last week. So the process now splits out in several directions in a way.
The job of me and Adam now is to show that this isn't just a theoretically nice idea, but we can actually do it for real and with our actual detector, with our actual experiment, because that's the point of the whole thing. It's an experimental technique, so make it work is the challenge. So our detector is called Atlas, and it's one of two general purpose detectors at CERN. So if you imagine this is CERN here, what it does is creates a load of protons in the accelerator complex there, and it fires them into this 27-kilometre round tunnel, which they're going round, one bunch of protons going one way round, one bunch of protons going the other way round, and they collide in the middle of Atlas and our rivals CMS, who are over on the other side. And there are also two other more specialised experiments as well, LHCb and ALICE. So the protons collide head-on in the middle of Atlas, and they give us all this stuff, and hopefully one of the things they give us is the Higgs. In general, physics experiments are about, we have some ideas about the way the world works, and we want to go and see if the world is anything to do with our ideas or not, and the only way of finding out is going and looking. It's a little bit different from just observation, although it starts with observation. So if you, when people were trying to understand life, and the first thing you do is you go and you count the species and you work out, or if you want to understand how the universe works, you go and look at the stars and count them and see how they're distributed. But in the end, you have enough data that you start spotting patterns and you build theories and you try and understand how the things came to look like, what they look like, and what might they look like next, where are they going, how does the dynamics of the whole thing work. And in order to do that, you construct some ideas, and then the only thing to do is go and try and find a way of seeing whether this idea has got anything to do with reality. Does it just happen to be, is it one of many possibilities that explains what you've seen, or has it got some more validity than what you've just seen? Does it have any predictive power? And the only way to test predictive power is to go and do something new. And doing something new gets increasingly hard, which is why in particle physics, in fundamental physics, to do something really new, because we've obviously been looking at physics and fundamental forces since Archimedes and beyond. I mean, Newton was maybe the father of modern ideas about forces, and Einstein brought it further. So we've been doing it a long time, so a lot of the easy experiments have been done. So what we're trying to do is go to really high energies and really short distances to test the theories and develop new theories. So it's quite a big deal to do this. That's why it's exciting, but nothing comes free, and this is a huge amount of work and a huge investment of time and effort and money to build these experiments. But that's why we do them, is because without the experiments, really, we're just philosophizing, and science is more than that. Science is about testing our ideas against nature and using nature to show us new ideas as well.
If it exists and it is the mechanism by which things in the universe get mass, then we should be able to observe it at the LHC and see that it exists, and that's how we'll confirm that that is the correct mathematical model for describing physics in the universe.
That makes it sound a bit like we're looking for the last piece of the jigsaw puzzle, which isn't a view I really like, because until you've found that last piece, you don't actually know whether the jigsaw puzzle finishes there. It's a corner piece, and maybe it carries on into another whole, we're only looking at a small part of the jigsaw puzzle, and there's a much bigger puzzle out there.
We're always curious about what's around us. That's part of what makes us special. And by being curious, sometimes we discover things that are useful as well to us. And if we didn't have that basic curiosity, we certainly wouldn't be here where we are today.
Finding the Higgs is the biggest problem in particle physics at the moment. I don't think there's any doubt about that, or at least understanding electroweak symmetry breaking, if you wanted to be pernickety, but that's the biggest deal at the moment. Atlas and CMS are the biggest, most important particle physics experiments of a generation. No doubt about that, no one would argue with that. This paper could have a huge impact on what they do on their most important job. And that's a big deal.